Welcome to this video covering the topic monocular vision-based and ultra-wideband-based techniques for indoor positioning. This is Chong Huang from National Zhongxin University to do this presentation, together with Professor Guanghao Lin from National Formosa University. In this video, two indoor positioning techniques will be presented. The first one is a monocular vision-based landmark matching scheme for identifying absolute indoor locations. The second one is the relative positioning scheme, mainly for automatic following functions based on ultra-wideband technologies. Both schemes are cost-effective solutions and can be easily adaptable to different applications. The first position technologies uses image matchings to find the absolute indoor locations and has the following features. First, low deployment cost, no hardware cost in system deployment. Second, easy to use. No video clip is needed in positioning, and just one monocular image from an arbitrary angle is sufficient to achieve the positioning. Third, low computing complexities. It is free of the time-consuming CNN models, trainings, and does not count on semantics information. And the various optimizations such as pre-computed landmark features, extractions, and image screening schemes are applied to reduce the matching effort up to 91%. The last one is accuracies. Correct landmark identification rate is up to 90%, and the positioning error is less than 1 meter. The first step in positioning is constructing a landmark image database. Given a target field such as a shopping store, a set of anchor points are selected. For better matching results, these anchor points should be chosen from more static environments and avoid glass self-laminated areas. For each anchor point, a landmark image, which is a panoramic view of the surroundings, is taken. This can be accomplished by image stitchings. These landmark images then form a reference database for matching, and it's the extracted informations, not the original images, are stored. A landmark image requires extra depth information. To expedite the process of depth annotation, a LiDAR camera is employed. It can obtain RGB and the depth image simultaneously. Alignment of these two images is necessary for more accurate depth annotation. To find the locations, we first take a Photoshop from the current positions in any arbitrary directions. This is called the target images, which is then compared with the landmark image database. The positioning flowchart starts with the image screenings, then detailed matchings and location calculations. We adopt a two-stage approach to reduce the matching complexities. Stage 1 is histogram-based image screenings. Stage 2 is feature points-based detailed matchings. Finally, location and the direction calculations is performed by using the feature point matching results and the depth informations. In addition, an image preprocessing is performed to improve the screening results in stage 1. This is to combat the influence of the ambient lightings and to reduce the miss rate. In this slide, to the left, we can see the histograms of two images taken in nearby locations can be very different if no preprocessing is performed. To the right, the similarities stands out after preprocessing. The matching criterion is the Bhattacharya index between two histograms. We used the threshold and the local maxima to select the candidate views. The screening process can reduce matching effort by an average of 91%. Stage 2 performs feature points-based matchings. Feature points selection is resistant to scale and rotations variations. From these examples, we can see successful matchings even if the target image is partially blocked by actual peoples. For an experimental field in our campus, 27 anchor points are chosen. This table summarizes the results of 74 target image trials. If the displacements between the current positions and the nearest anchor point is less than 60 centimeters, the matching is basically error-free. As the displacement increases, the correct matching rate degrades. In the final step, the displacement and the facing direction of the target images are calculated. This is the calculation model based on multiple pairs of the matched feature points. We apply the triangulation schemes to determine the origin of the target and the relative angles. Experimental results indicate that the average positioning error is less than 30 centimeters, and the average facing direction error is only 5 degrees. We will next introduce the ultra-wideband-based triangulation schemes. These schemes features a low-cost approach for relative positionings. It is based on the time of flight information for distance calculations. Currently, it is implemented on an AGV to support automatic following functions. Relative locations between the AGV and the leading person is obtained by triangulation with 2 anchor devices mounted on the AGV and 1 tag carried by the user. Error compensation schemes is introduced to alleviate the variations of the TOF measurements. It can reduce the environment signal interferences, and the distance estimations error can be reduced from 25 centimeters to about 5 centimeters. This slide shows the system architectures. It has a Mac-based system controller, which is responsible for the motor control of AGVs and provides interface with anchor devices. The anchor device consists of a Raspberry Pi and an RF modules. The AGV can be equipped with ultrasound radars for collision avoidance. It also has preliminary path tracking and detour capabilities. Compensation schemes are employed to reduce the estimation errors of distance and angles. In both charts, the upper curves correspond to the uncompensated results, and the low ones are the compensated results. This shows the significant improvement. Okay. This is the demo video showing how the AGV are successfully following a moving tag. So we can see a user carry a tag to guide the moving of the AGVs, and the AGV follows the guidance successfully. Okay, we now summarize the potential application of the proposed image matching based position scheme. Okay, it is the low-cost solutions with no actual hardware in system deployment, particularly suitable for environments where actual wiring or fixtures is either difficult or unaesthetic. At the user end, only a camera-ready mobile phone plus an app is required. For better results, environments should exhibit sufficiently diverse backgrounds. Department stores, shopping malls, train stations, museums are some examples. It can serve for the navigations and the guiding purposes. It can also be applied to video slam for finding the initial location. For the proposed ultra-wideband triangulation scheme for relative positioning, it is a cost-effective kit that can be easily mounted on any guided vehicles to support the following functions. It can collaborate with ultrasound radars or IMU for collision avoidance and detour. Possible applications include automatic shopping carts, automatic golf following trolleys, auto following luggage, unmanned farm wagons. Thank you for viewing these presentations. Welcome to contact us for more technical details. And the following is the contact information of both authors.